Alright, so the next group of reactions that we're going to look at are decomposition reactions. So as you can probably guess by the name, decomposition reactions involve something decomposing or something breaking down. So we recognize decomposition reactions because they're the only type of reaction that we'll see that only has one reactant. Okay? So decomposition reactions will always only have one reactant, and that one reactant will decompose into multiple products. So we're going to go through several types of decomposition reactions, but you'll find that decomposition reactions are merely the inverse of synthesis reactions. So for each of the synthesis reactions that we discussed previously, we'll have the exact opposite reaction will be the corresponding decomposition reaction. So a lot of times if we just took the synthesis reaction and changed the direction of the arrow, we could turn it into a decomposition reaction. So let's go ahead and look at the first group. Okay, so the first group is the decomposition of simple molecules. So this is the inverse of what we call the direct union for synthesis. So this is the breaking down of binary salts. Okay, so ionic compounds that are made of just two elements. Water also falls in this category, and binary acids fall into this category. Okay, so let's look at some binary salts. So we can look at NaCl, for example. Okay, so if NaCl decomposes, a lot of times you'll see heat is applied. Okay, so you could see something like heat is applied and sodium chloride decomposes. So don't forget, when heat is applied, if that's written in the word problem, we must put the triangle over the arrow. Okay? So if a binary salt decomposes, we simply just break it apart. Na plus Cl. We're not done though. We can't forget that chlorine is special. Chlorine's diatomic. Then we go back and balance the reaction. Okay. So if the problem didn't mention the phase of the starting material, then we don't need to worry about the phase symbol for the products. So let's look at another one. Let's look at Mg. 2. If I said that decomposes after being heated, I could put the triangle to denote heat. My products would simply be Mg plus I2. And it's I2 not because it's I2 on this side, it's I2 on this side because it's diatomic. It's I2 over here because magnesium is plus 2, iodine is minus 1. Okay, so fairly simple for the decomposition of binary salts. We can show the decomposition of water. So water would decompose into H2 plus O2. If you had told me, or I had told you it was liquid water to start, we could put the L. Hydrogen we know is a gas. Oxygen we know is typically a gas. Okay, then we need to go back and balance it. So now I have a balanced reaction and I'm good to go. So binary acids, same idea. Remember, binary acid is just hydrogen plus a nonmetal here. So HF would decompose into H2 plus F2. We can balance the reaction. So the decomposition of binary salts and binary acids are very, very simple. You just simply break the molecule apart, and you can think about the reverse of this reaction as being the synthesis for this molecule. Okay, so nothing tricky here at all. So the second class we're going to look at is the decomposition of oxyacids. Okay, so not binary acids, but the acids that contain oxygen here. So we can have something like H3PO4. And the problem can tell you that it decomposes. Okay, so we might have some kind of catalyst above the arrow, but we'll just leave that blank for now. So if you remember, the synthesis reaction that formed acids involved us using the gas-ion charge. Okay, so we know in this process, for the synthesis of an acid, you convert a gas to an ion. So for the decomposition of an acid, you will convert the ion, the polyatomic that makes the acid, into a gas. So if you go to the table and you find phosphate PO4 negative 3 in the gas ion chart, you'll see that it corresponds to the gas P2O5, and we can go and label that. We know it's a gas. And plus, I know my other product is going to be water. Okay. So if you think about it, this is the exact opposite of the synthesis reaction that we learned. So hopefully these decomposition reactions shouldn't be difficult at all. Once you learn the pattern for the synthesis reactions, you know the decomposition is just the exact opposite of this. So we'll go through one more of these. Nitrous acid would be HNO. N2O2. So I go find nitrite, NO2, in the gas ion chart. I see the gas that corresponds to that is N2O3. Label that. My other product is water. Okay. Something I didn't do up here that I should have, I need to go back and balance this reaction. I need to balance this one as well. So go ahead and balance those on your own and see what you get. Okay, so hopefully this is what you got for balancing the reactions. Go back and make sure you have the same number of each atom on the side. And if you didn't get this, go back and kind of figure out where you went wrong on those. Another possible alternative is you can put 1 in front of all these. If you need to do that, that's perfectly okay. Okay, so the decomposition of acids, again, shouldn't be difficult. You should recognize it's an acid and remember your pattern from the synthesis reactions. So next let's look at the decomposition for metal hydroxides. So I could have something like MgOH2, or I can have KOH, so metal hydroxides. I should recognize these immediately as being decomposition reactions, okay, because there's only one reactant. So all that can happen is it has to decompose. There's no other chemistry it can do here. So if you remember from synthesis, to form a metal hydroxide, you need a metal oxide plus water. So when a metal hydroxide breaks down, you're going to get the metal oxide. I check my charges, +2, -2, I'm good to go, plus water. Okay. And again, if it had explicitly told me in the problem the phase of the starting material, then I could list the phases all the way through. But let's just say it didn't tell me explicitly here, so I could go ahead and leave those off here. So then I'll go back and see if it's balanced. 1 magnesium, 1 magnesium, 2 hydrogens, 2 hydrogens, 2 oxygens, 2 oxygens. I'm in good shape. So potassium hydroxide, I recognize it's decomposition. There's only one reactant. I see it's a metal hydroxide, so I know a metal oxide plus water will be my products. I go back and check my charges. +1, -2. They don't cancel, so I have K2O here. I go back. I balance the reaction. 2 potassiums, 2 potassiums, 2 oxygens. Excuse me. Yeah, 2 oxygens, 2 oxygens, 2 hydrogens, 2 hydrogens. I'm in good shape there. Okay. So again, just as we had for the synthesis, we can talk about what's listed as number 4 in your notes, but rather than giving the generic idea, we'll look at number 5, so you can skip number 4. Number 5 is just a more specific subset. Excuse me, let me back that up. Number 5 is a more specific subset of number 4, so we'll focus on number 5 here. So reaction type number 5 is a metal carbonate, a metal carbonate, so something like MgCO3 or K2CO3. If you remember from the synthesis problems, how you made a metal carbonate was from reacting a metal oxide plus CO2. So when a metal carbonate breaks down, you will get a metal oxide, so MgO plus CO2. I check my charges, +2, -2, so I'm in good shape there. I see it's already balanced and I'm good to go. So potassium carbonate, it decomposes. Again, we could have a triangle here. It could say 100 degrees Celsius. It could say a lot of different things. So we'll just go with whatever it has written in the problem. We'll be sure and write that above the arrow. So the metal oxide, so KO plus CO2. Go back and check my charges, +1, -2. Those don't cancel. So I need to write K2O there. And you'll see the reaction balances out quite nicely there. So then the last one, type number 6, we have metal chlorates decomposing. So we'll do NaClO3, and then we can do BaClO3 too. So we remember that to form a metal chlorate, I need a metal chloride plus oxygen gas. So when these compounds decompose, they will decompose into those two compounds. So we'll produce a metal chloride, NaCl, +1, -1, so I'm in good shape, plus O2. So I can say this started off as a solid, so NaCl would be a solid, O2 would be a gas here. Barium chlorate, I need the metal chloride, so BaCl2, say it's a solid, plus O2 gas. I didn't mention it, but we should go back and balance up here. I got ahead of myself there, so let's balance this reaction. I need to put a 2 there, I need to put a 2 there, I need to put a 3 there. So there's 2 sodiums, 2 sodiums, 2 chlorines, 2 chlorines, 6 oxygens, 6 oxygens. So I'm in good shape here. So if I look at this problem here, I need to go ahead and balance this. I have 1 barium, I have 1 barium, I have 2 chlorines, I have 2 chlorines, I have 6 oxygens, so I put a 3 here, so I have 6 oxygens as well. Okay. So hopefully, I know I went through that very fast, but hopefully the decomposition reactions will be very, very simple. And they will be simple for you if you learn the patterns for synthesis reactions, because decomposition reactions are just the exact opposite of those synthesis reactions. So there's really no need to really even learn decomposition as another category and learn the rules, because as long as you know the synthesis rules, you can just flip the synthesis patterns around backwards and you have decomposition reactions. Again, just as you don't forget to use the gas ion chart when you form a oxyacid, don't forget to use the gas ion chart when you decompose an oxyacid. Okay. Trying to think if there's anything else. One other thing, don't forget if you have an ion compound, go back and double check your charges. Okay, don't write KO. Go back and actually write +1, -2. Go back and cross the charges and make sure you're good there. And then, as always, don't lose easy points. Go back and make sure the reaction's balanced. Okay, that should be the last thing you do on every problem.